אנחנו מקליטים.
כן. מה העניינים? בזמן שהאחרונים נכנסים אני אנסה כאילו אולי כזה להבין מי הקהל שעומד לפניי, זה תמיד טוב לדעת לפני מי אתה מדבר. אם גדולים לך בתורה זה תפלצת. מי פה מגיע מהאזורים התיאורטיים יותר? אקדמיה, מפתחים, פרודקט, משקיעים. מה, מאיפה, כאילו סתם נכנסתם למיטות ומצאתם... מה נשאר? מה אתה נגיד עושה?
אלגוריתמיקה.
איפה?
היה מחשבת.
בתור מפתח אלגוריתמיקה.
אני?
כן, למשל.
מובטל.
מדהים. בהייטק.
מובטל בהייטק.
זה נראה לי אחד החלומות, כאילו, נכון?
אבל גם אלגוריתמים.
אפשר לשאול אותך?
זה בעיקר NLP.
מגניב. יש כאילו, אפשר להיות בספקטרום של ההרצאה הזאת יותר באזורים התיאורטיים, יותר...
Excuse me, is there a chance to switch to English?
There is a chance to switch to English. I'd have to apologize because my English is not outstanding, but I think like if you want to be a startup nation, we should be able to speak English for the sake of this nation. So, there are lots of ways to do this talk. This one would be talking about how to boost your GAN training with TensorFlow and Tensor Cores. Tensor Cores, if you haven't heard of, we're going to talk about today, is an NVidia technology that boosts your training. It does not only apply to GAN training, we can do also NLP with it, we can do LSTMs or convnets, but for the most part, you'd find a lot of use case for Tensor Cores with GANs. And I'm specifically going to talk about how to do this on TensorFlow and on Google Cloud. But this is actually something that you would be able to do on your personal GPU, whether it's installed on your personal computer or your cluster or in any other cloud platform. So, generative models. What are generative models? The basic idea of generative model is to take some noise, or let's call it a latent variable, or latent vector, and from this noise to create articles, they're actually samples that you would usually train up on a classifier. For example, for the sake of this זה נורא קשה להחליף אנגלית, אבל אני ממש אשתדל. אם נראה שזה הולך, אז אני אחזור לעברית. So basically, for the sake of this conversation, I would mostly be talking about images. So the idea of generative models is to take some random noise and then to put it into kind of a machine and generate something of a specific probability distribution. It can be, for example, images of geese. And there are several models, several types of family models. One would be autoregressors. You could also think about variational autoencoders. And this conversation is going to be focusing on generative adversarial networks. And generative adversarial networks started like, were first introduced I think in 2014, but the first applications were only like visible in 2015. And these were kind of the vanilla results of generative adversarial networks. We're talking about this as an attempt to create an image of a flower, and this should be, I think, a flying bird. This is like a bird in a nest or something. The first initial results were not that outstanding, but the whole concept of a computer that can imagine or can generate data and not just tell us if it's a bird or a duck was kind of groundbreaking. And with time, we have seen a lot of progress, and there are lots of ways to make improvements upon the vanilla GAN. I'll be discussing about mostly a technology, a way to improve the training of GANs, but I will be also mentioning a few other techniques. So what can we do with GANs today? So nowadays we're able to produce really, really high quality images, really high definition. This is an example, I think, from last year that created. All of these are computer-drawn anime figures, very high resolution, very nice. You cannot distinguish that was not created by a human being or an animator. It was all created by a computer. If you know the content or completion in Photoshop, that is not based on generative models. That is what based. Actually, the person who invented it, I used to know her. She's a professor at Technion. Forgot her name. But you could do these content-aware completion of data using GANs. This is an example where you just hide this block from the computer and it autofills it. If you can see closely here, it says hotel, and the computer obviously did not know to put an L here. But the overall content seems pretty reasonable. There you can see it completed a tree, and I don't know what that's supposed to be, like it's smashed dog or something. And even some companies, in February I've seen a presentation by LMVH. It's Dior and Louis Vuitton. And Louis Vuitton is actually creating new samples of new patterns and samples for their bags collections. You can find patterns that were never have been created by a human being. All of them are generated by a computer. And you can actually see applications of generative models in the textile industry. So a lot of, I think that most of the applications that I've seen were relevant to computer vision, although you can basically generate any kind of probability distribution if you know what you're doing. So I've been talking about GANs, but what are the GANs? So I'm going to present the vanilla way of GAN, and there are some complications to the vanilla form that we can mention later. But this is like the vanilla GAN that was presented in 2014. And the idea is basically to have two networks. One of them is a generator, and the other one is called a discriminator. And the generator has a very specific role. It has to take noise and output. I said we're mainly talking about images, so I'll just refer this as images. Let's say I have the MNIST data set, so I have this training set of images. So the generator would try to generate pictures or images that look like the images of the digits that are in the data set, not necessarily exactly like the images that you would find. So it would look like very similar, so you wouldn't be able to distinguish between an 8 that was drawn by the computer or an 8 that appears in the data set, but it's not necessarily identical. Or you would rather it not to be necessarily identical. And the other network that we were talking about is the discriminator. Now the discriminator is basically a convnet, a very standard convnet that accepts a fake image or training or a real image as an input and tries to output if it's a real or fake. This is very, very common use case of convnet to have like an input image and then try to assign it to class. And how do you train this kind of system? So this is why it's called Generative Adversarial Networks. Basically, these two networks competed against each other. The first one, let's start with the second one. The discriminator, as I said, has to distinguish whether it was a fake image or a real image or a genuine image. And it's really, let's say I have a well-trained discriminator. I would train it on the MNIST, and I would put in a fake image, then it would probably be very, very easy to distinguish. So the generator has to learn how to trick the discriminator in order to confuse his labels. So basically the loss for the generator would be the negative, for the most part, would be the negative loss of the discriminator. So the discriminator is given a set of samples of fake and real images, and it has to distinguish between them, and it has a loss over this image, over this data set, passes the loss to the generator, and then the generator tries to learn new techniques to improve the image generation in order to create images that are more and more like this training set. Yes?
So you said that you would have a discriminator, but if you're training it on NVists, it would just know how to separate the digits, and it would be very good at telling you if it's from the data set or not from the data set, right?
Yeah. Yeah. Okay. So what I was mentioning, what I was referring to, what I was trying to say was that if I have a very good discriminator, then basically, and this is what one part of one problem in training generative models or GANs is that if the discriminator is very good at what it's doing, then it won't be able to. The generator would never be able to understand how it should change the parameters in order to generate better models. So the training of these two kind of has to go together. You cannot start with a very good discriminator. Both of them has to be initialized kind of to the same random values at the beginning, and then when you train them gradually together, the discriminator gets better and better, and then the generator can learn gradually how to generate images. Okay, if that was not clear. So let's look at how the training process would look like. So this is the images that are generated, I think, for an AC GAN, a kind of GAN that also learn to classify the images. I'm giving it a classified data set. And what you can see here that over time, the images that are generated by the computer kind of get the shape of what you can tell as a 4 and a 1 and a 6 and a 0. So this is basically how it looks like during the training. And let's talk about what specific difficulties do we usually have when we're training generative models. Okay. So first of all, as opposed to regular classification or regression problem, we don't have a very good function that could tell us if we're doing right or wrong. Because there is no function that can tell us if this 9 looks like a real 9. We are actually kind of learning this function within the discriminator. So part of the solving the problem is actually learning how to solve the problem. And that's really not a good practice for science. But it brings very good results. So it's kind of a tricky way that in order to solve the problem, you have to learn how to solve it. It's like when they tell you, how do you search for love? You don't search. When you go, when you find it, you know it. This is why I'm single. Okay, so and so you don't have a very distinct, simple way of finding if you're doing a good job. Another thing that we mentioned before was that you have to train them together, because if the discriminator is really good, the math behind what I was saying that the generator would not know how to generate better images is that the gradients would basically all be 0. Because no matter what the generator is generating, it's always, the discriminator always telling him, no, I can figure it out pretty easily, this is all fake. So it means that no matter what you're changing, you get the same result, the gradients are 0. Another problem that you might have is that it's a very complex target distribution. As opposed to when you're trying to estimate a probability distribution, when you're training a classifier, the generator actually is trying to imitate a very complex probability distribution, and basically talking about images of people or images of cats or images of digits. It's a much higher dimensional complex probability distribution that we're trying to imitate with respect to, I don't know, cross entropy of probability distribution in a classifier. And another thing that we also encounter is the quality variation trade-off. If we were able to overfit on our training set, we would always generate images that are look exactly like the images that are in the training set. But we don't want that. We want a general model that can generate new images of digits or of human faces that is not exactly the same to the images that are in the data set. And let's just see. Let's see, I closed the tab. It's called this person does not exist. Have you seen this? Must have. So these are all images. When I kind of refresh it, I think that when I refresh, I get a new image, and all of these images, I think that are generated online, like per my request. So these are all people that do not exist. These are images that are generated by Generative Adversarial Network in a technique that we're going to talk about in the next few slides. And you can see here some like errors that the model have. Question?
How do they know that these people don't exist, that they're not actually
part of the data set? You can actually search. It was not built on a huge data set. You can actually search for this particular image. This person does not exist in the image. And they also, I'll be mentioning it in a few seconds. Okay, so a major advance in generative adversarial network training was made by NVidia last year. In an article that they call Progressive GAN Training, they were able to create images of celebrities that do not exist. For many people, if I ask you if you know these people, you would say that they look familiar, but these people are not actual celebrities. These are just generated images from a huge data set of celebrity images that was from a GAN that was trained on this kind of data set. And what NVIDIA did is that they understood that you don't have to, and another thing that I forgot to mention, that the images that I showed you before are really high resolution images. They're not just 64 by 64 images or 32 by 32 images of digits. These are really high definition images. So what NVIDIA figured out that the gradual process, the quasi-statute, of this process is extremely crucial towards the training. You cannot go and directly train the 1024 squared pixel images, but you have to go through first 4x4 images, pixel images, and then 8x8, and then gradually add more layers in order to be able to produce by the end of the training process very high definition images. So this is like the kind of scheme of the training. You have the generator here. It accepts a 4x4 latent matrix. It's what we call the noise. And then the discriminator accepts this 4x4 matrix and then tries to output a blurred image of this data set. And then with time, we just give them more and more complex images. So this is kind of the progress that was made, kind of summarizes the process that was made throughout the last years. So these are another classic example of generated images of hotel rooms. So in 2016, these rooms were kind of smudged or disoriented. And in 2017, you could see some kind of an improvement. But then our refers to NVIDIA's progressive GANs. Very high quality of also hotel rooms that are all generated with this technique. So when we're training GANs, or generally when we're training neural networks, we have a few ways to increase the training speed. And why am I mentioning it was that this GAN was trained for over 10 days in order to achieve these kind of results over multiple GPUs, very powerful GPUs. So it's extremely difficult to do research or you do R&D when you have to wait 10 days and only then you can discover if your results are real, if you're going in the right directions, especially when we're talking about GANs, that the loss is not really telling us anything. If I'm taking a look at this very schematic plot of the loss, then you can actually see that at the beginning, the discriminator loss is extremely high, and the generated loss kind of increasing towards the end of the training. But these numbers don't really tell me anything. Looking at the loss when training GANs really don't mean a lot. They can kind of indicate which part of the system is stronger right now, if it's the discriminator or the generator, but I cannot know like what is the quality of images that I'm getting from this kind of loss. So it's not really comfortable to do research when you have to wait 10 days in order to get results. So let's say I was training just a regular network. What could I do to increase the speed of the training? So first of all, I could increase the batch size. But when training very high resolution images, I would find out that it's not really easy to put in a lot of, GPU memory has a strict limitation, and it's not very easy to pack a lot of high resolution images to one batch. So it doesn't really work for high resolution training in GANs. I could think of ways to distribute my training over several GPUs, and it only complex the problem. Another thing would be to increase the learning rate. But as we mentioned, we don't want the discriminator nor the generator to make very large moves, like very large steps, because then if the discriminator makes like a substantially large step, the generator might get lost in the gradients. It can end up in the vanishing gradients. So that would not work for GAN training. Reduce the I/O overhead. For example, if I have overhead from reading from the disk or network or something like that, that could also work for GAN. Change the architecture. Optimize for the architecture. Lose unnecessary weights, lose unnecessary layers, reduce the size of the layers might also affect. And obviously, the main key point of our conversation would be how to improve the hardware. So we can use improved hardware in order to train GANs. For example, more RAM would result in being able to increase the batch size. Or if our GPU can perform more teraflops per second, then we are able to train faster. So for this, NVIDIA came with a new technology that is called Tensor Cores. What are Tensor Cores? Basically, it's a way to, they're registers on the GPU that are able to perform 4x4 matrix multiplication and some addition. So it multiplies 4x4 matrices and then just add them, and that's all in a single clock. As opposed to the previous architecture, that if I wanted to perform the multiplication, I would do it vector by vector and then add it later. Another difference that you can see is it's not only faster because it's doing the 4x4 matrix multiplication at once, but the multiplication itself happens a little bit faster. And that is thanks to the architecture that NVIDIA chose, and they're representing the matrices by float 16 numbers or variables, which can reduce the overhead of the computation during the training. So this is basically all what Tensor Cores are doing. They're taking two matrices, 4x4, in a float 16 representation, doing the multiplication and adding them to a running sum of a matrix multiplication, which can be a float 16 or a float 32. And for who don't know this, most of the operations that we do during training of neural networks are basically of this type. It's a multiplying matrix of weights by matrix of gradients or something like that, and adding them to a running sum. So it's really highly optimized to many of the operations that are running in the background when we're training deep learning networks. So why did NVIDIA choose to work with floating point 16? So the first one is a little bit tricky. I would say that reducing, it's kind of from their slide, so they're saying it reduces arithmetic intensity. And what they're saying is that we created for you and highly optimized registers in the GPU that are able to perform this matrix multiplication. So if you're using floating point 16, you'll be able to use these registers, and by this reducing the training time. And that's not really impressive. The second reason that they're saying is that you can reduce the memory bandwidth. You can think of it as when you're downloading 720p movie or a 1080 movie, that 1080p movie, the small representation of the movie would result in a faster speed, download speed.
But you have to downsample it, no?
Yeah, and we will be talking about how we do this change of the resolution for deep learning neural networks. And another thing that it allows us is we were talking about a way to increase the batch size, but increasing the batch size resulted in a limit on the total memory signature that we have on our GPU. So if you're using reduced representation of the images or the training set, we are able to put more data in our batches, and then by this increasing the size of the batch. The disadvantages, obviously, of using floating point 16 would be that we lose part of the representation. So in the next slides, I will be talking about how exactly to do that in order not to lose too much representation and not to reach to the point that we lose enough representation, for example, in the gradients, that the gradients would simply all convert to 0, and we will experience vanishing gradients. So let's look at a computation graph of a neural network training. You get an input, you do the forward pass, you compute the loss, you transmit the loss to the backward propagation process, and then you update the gradients, you update the weights, both to the backward and to the forward model. It's basically the same thing, not here, as we'll see in a few minutes. And then you input more data and do this whole cycle over and over again until you converge. The next slides would be to choose which part we want to do in floating point 32 and which part we want to do in floating point 16. This whole process is called mixed precision training because as it is right now, it is all done in float 32, but we will try to replace some of these blocks with a floating point 16, and this is why we would call it mixed precision training. So I divide all of the operations into 4. Weight update, activation, reduction, and matrix multiplication. Let's see, what are these operations? So weight updates. We all know that neural networks have weights. These are called, usually marked with a letter theta. And these weights has to be both saved and updated during the training. So when I'm training my network, as it turns out, while NVIDIA was developing their neural architecture, they were measuring the probability distribution of weights in the network during the training. Like to actually see what are the sizes of weights that they're getting during the training. So for the most part, floating point 16 was substantially enough to represent all of the weights. Some networks required to represent the weights in floating point 32. So just to be on the safe side, we would keep the weights as floating point 32. What was necessary to do was to represent the gradients of the weights in floating point 16, in floating point 32. And why is that? Usually, especially when we're talking about GANs, we use a low learning rate. So we multiply the gradient by a small number, like 10 to the minus 5. So we actually are very you're shrinking the gradients of that are supposed to be added to the weight, to the weights. And when we're adding to the weight, representing in floating point 32, a very small number, and then we trim this number to floating point 16, it turns into 0, and then we don't have enough representation. We don't have enough representation to our gradients, and then we get vanishing gradients. Basically, all the gradients are 0. Nothing happens. We just wait, and no updates are recurring. So the weight part, we're gonna basically want to do both the weight updates and both the weight storage in floating point 32. Another operation that we usually do is compute activations. For example, after we updated the weights, we would like to compute a ReLU or a sigmoid or I don't know, or scaling or addition of a constant. All of these operations were found to be substantially enough for floating point 16. This does not include activations that are kind of non-standard, like doing an exponent or a square or activating a log, because these functions tend to have that the f of x is much larger than x. So for these kind of activations, we would use floating point 32. But if you're using kind of the standard activation, it's a ReLU, sigmoid, tangent, hyperbolic tangent, scale, addition, all of these are pretty are enough. For all of these, floating point 16 is enough. Reduction operations, for example, summation. When we're doing L1 norm, we actually are adding all the weights, all the vector weights of a layer. So when we're adding all of these numbers, which can be pretty small, we can end up with a large number that cannot be represented in a floating point 16. So for this, for all the reduction operations, L1 norm, L2 norm, softmax, we would all want to do them in floating point 32 because we need more representation for this kind of operation. And another operation that we have is a normalization and loss. These kind of operations are basically a combination of a few other previously mentioned operations. It can be reduction, it can also be the weight multiplication. So if we're doing reduction to calculate the loss, then we also want to do the loss in floating point 32. And to finalize this, one very, very significant operation that we do, especially in GAN training, since we mentioned that most applications in GAN are related to computer vision, is multi-matrix multiplication, very common in confidence. So these were found to be perfect for floating point 16. No overflows were found. And just to mention where I'm getting these kind of imaginary facts about weights being represented in 32 or 16 bits, what NVidia did was to run multiple experiments on very famous networks like Resonant 50, VGG, or LSTMs, and kind of collected statistics about what are the weights that are generated during the trading. So this is what they find out. For the weights, this kind of distribution. For the activation that they got this distribution, the weight gradients is this one, and the activation gradient is this one. Someone could someone kind of guess what is this spike here? What is this kind of strong number here?
From value, from zero value?
Yeah, it's a zero of ReLU. Yeah. So a lot of the networks use ReLU as an activation, and this is the reason that you see like that the weights can be you don't see a lot of zeros in the weights, but when you're calculating the activations, you're actually getting a lot of weights because they're below the threshold. So this is kind of explain what is the difference in the distribution between weights and activations. If you had to think like, why am I even mentioning this fact? So what you're seeing here in blue is the zone that can be represented in a floating point 16. And as you can see, the weights are usually okay within this range. The activation is kind of okay. Why am I not worried about this one? Because it's 0, yeah. Because if I cannot represent it, it would be trimmed, and then I for the worst case, I would just end up with a 0. And the weight gradients are kind of edgy, and the activation gradients are a real big problem because, as you can see, they cannot be represented within the floating point 16 range. So, can anyone think of a solution to what I can do with these two? Shift down. Do you have an idea of how?
Log?
A log could be a good idea, or just multiply them by scale. So, since we're only talking about the weight gradients and the activation gradients, and all of the computation is done with using the chain rule, then multiplying the loss by a factor and then dividing the loss by a factor would not affect the numbers themselves. So we can kind of shift our gradients towards the zone that we want to have our data in. So the idea would be to multiply the loss by some constant s, to do all the gradient weight and activation weight updates with this scaled loss, and then unscale it after we finish calculating the gradients. So this is kind of the algorithm that NVIDIA offers. There is another sophisticated version of this algorithm that does, because I have to kind of, it adds me another hyperparameter to choose in the beginning of the training. So there is a way to discover an optimal S during the training, and NVIDIA mentions it in the blog post that they have. All of this is in the link. So I have the concepts. Now I want to go through how I'm going to change my TensorFlow code in order to support mixed precision training. I would mention that when I started doing this, I had to manually change the code in order to support mixed precision training. Now all you have to do in TensorFlow 2, and I also think that in TensorFlow 1.3 or 1.3, whatever. But in TensorFlow 2, it's for sure. You only have to activate a flag, and you have mixed precision already implemented. So this is if you're working in a previous version, not supported version of TensorFlow, you'd have to make all of these changes. But if you're transforming to new TensorFlow, then you would easily, you just get it for free. So let's look at a very, very, very simple network. We have a function here that is called build forward model. We are defining the input layer. A top layer does convolution, and then we have another layer that does batch norm, max pooling, reshape, and eventually dense. This is like a very reduced convnet, like the simplest convnet that I could think of. And we're returning the top layer, which is just a dense, flattened layer. And we take this function that I mentioned before, which is called build forward model. It returns a tensor. So this tensor is then put as the input of this logits layer, loss optimizer, grad vars, train operation, and then we return the inputs, labels, loss, training op. This would be the whole model that we have. This is like the core forward propagation model, and this is all of the loss part of the model. And the last part would just be writing a loop that does the training. So this is like hardcore TensorFlow. You can also do this in Keras, but this is how we would write it in TensorFlow. In TensorFlow 1 until like 1.3. So mentioning again our computation graph, the computation graph that I built is absolutely coherent with what I have here. It's an input that goes into a forward model, computes the loss, does a backpropagation, update the weights, compute the gradients, update the weights. The weights are updated into the forward and the backward model, and then new data comes in, and we do this over and over again in each batch. So the first change I'm going to make to my code in order to make it work with Tensor Cores, and very important to mention, I kind of forgot about it, that you don't have to explicitly call Tensor Cores. Whenever you have an operation that is float 16, the GPU would automatically refer it to the Tensor Cores. So the first operation would be just to cast to float 16. And let's see how it would affect our model. Basically, all of our model currently would be just in floating point 16. So this is what I did here. I added here a cast before the cast to the input before it's going to the forward model, and it paints all of our model in green. Now that is not what I wanted, because I already mentioned that I want to keep my weights in floating point 32, and I want, especially my weight gradients, I want to do them in 42, and I want to calculate the loss in floating point 32. So it's not really what I wanted. So let's do another casting. This time after I'm calculating the dense layer here, before I'm calculating the loss. Let's do a conversion to floating point 32. And how would that change our graph? So something really interesting happens here. I'm doing the casting before I'm calculating the loss. But then TensorFlow would automatically add here another cast to floating point 32, because this and this refer to the same variables. So immediately it would cast back after the loss would be computed. It would immediately cast back to floating point 16. So it's kind of an improvement toward what I wanted to do in the first place. This one is a little bit more tricky. In the backend, TensorFlow has a function that is called getVariable. It is called mostly when you're calculating gradients. This function is overriding the getter that you see here. Basically, what I'm doing is I will be passing this getter as a custom getter to the model, and what it does is that enforce that all of the trainable variables are going to be kept in floating point 32, and if they're not trainable, then I'm going to choose the data type that was defined during the graph, when I built the graph. So it's kind of tricky on how I did this, but you don't have to worry. Just have to either copy paste this function, or if you're using TensorFlow 2, just raise the activate mixed precision training, and then you'll be okay. So I'm using this custom getter here in this variable scope block that I'm defining, and this function would enforce that all of my weight gradients, weight parameters, will be kept in floating point 32 by simply doing the cast on the gradients. So this is, for the most part, everything that I wanted to have. Another small trick that we mentioned before is the loss scaling. So I can, let's say I have a fixed loss scaling and I don't want to change it throughout the training. So I picked a number of 128. So I have a loss scale here. I'm applying this scale to the gradient variables tuple that we have here. And then after I compute the loss, I'm just applying the division by the same scale. So this is how it looks like. After I calculate the loss, I multiply it by a factor, and then after I calculate the gradients, I divide by the factor, and then the weights are updated by the right number. So what you see here are all scaled steps of my training process. As I mentioned, this finishes everything I want to do. I wanted to do. This is a full mixed precision process of training. If you've done this, you should be able to experience significantly faster training process. And I would show you some results from experience that I did with generative models. As I mentioned, going to TensorFlow 2, this is all you have to do in order to activate mixed precision training. But if you're using some kind of a special architecture, non-standard loss functions, then you might have to go deeper into your code and transform it in order to have because you might experience vanishing gradients or exploding gradients or something like that. So it's kind of important to know what's running in the background when you're activating mixed precision training. So this is a short experiment of what I did with GAN training. It's all in the blog post that DoiT published. We used the quick draw dataset. If you kind of know this dataset, Google asked people to draw sketches of bees and over 1,000 different articles. All of these were collected to 32 by 32 or 64 by 64 pixel images. Not sure about the number, perhaps even larger. So we tested these with two GPUs that do support the Tensor Core technology. It's called the Volta architecture. And one GPU that does not support the Volta architecture. We wanted to see if mixed precision would affect in any way a GPU that does not have a Volta architecture. The obvious answer was no, but we just wanted to make sure what it does to the training. As mentioned, the data set was 10 classes from the 10 classes of more than 100K images. We use an AC GAN, auxiliary classifier GAN. This is a GAN that, additionally to the generating to the GAN process, is also training a classifier, which kind of helps it converge faster and to better results. Not the cutting edge results in GAN, but fairly easy to train. The parameters that we wanted to test is how batch size is going to affect, how mixed precision versus single precision is going to affect, and what is the importance of the GPU model, how different GPU models will converge. All of this was done on Google Cloud using Google Cloud. Used to be deep learning VMs, now it's AI notebooks. To basically say what was the main difference, these are the results we got after 7 minutes with mixed precision on a specific configuration, while after 7 minutes of the single precision on the same GPU with the same batch size, the model did not even converge. But that could be easily cherry-picked, right? So let's see some more insightful statistics. First of all, we measured for a batch size of 128 samples. We measured what is the difference in mixed precision versus single precision. So you can see that for T4, which includes the Volta architecture, you see some reduction from just around 50 to 40, and in V100, which is also a GPU that has the Volta architecture, you see a slight improvement. And for the P100, you actually see that mixed precision increases the training time. And that is mostly contributed to the casting, I guess.
P100 is the one without the architecture?
Yeah, P100 does not have the Volta architecture, so I'm just doing conversions and castings, and it does not result eventually in an improvement, and that's good because this is exactly what we were expecting. So this is a fairly small batch size. We wanted to see how it affects if the batch size is increased. So what you can see is obviously the total time is increased because we are going through many more samples, but the difference between doing mixed precision and single precision is significantly higher. Significantly reduced here from almost 700 milliseconds per batch to just over 400. And that is pretty impressive. Here you can see that for P100 you don't see a lot of difference, and for V100 you also see a very significant difference. The next thing that we wanted to check is the effect of the batch size on the overall training. And this was all mixed precision. So obviously, and it's really clear, that when you increase the batch size, if it fits into your memory, you're going to train faster, right? There is no surprise about it. As you can see, for 128, you get about 350 milliseconds per batch, and then it decreases as we increase the batch size. Not a big surprise. What was an interesting point was to see what was the difference between single precision and mixed precision per batch size. And you can see that the most significant reduction was in the higher batch size. As much as the batch size is increased, the effect of mixed precision is more perceivable. You can.
You said this before, didn't you? The previous graphs you showed the first set.
Yeah, but this one shows like that it's that it has a trend. It's not like it wasn't like jumping from 128 to 2048. It actually has a trend. So we picked the batch size of 2048 for both single and mixed precision for these GPUs, and we converted this to money. How much would it cost us to train on 1 million images with a batch size of 2048 on a T4, on a B100 and a P100 with mixed and single precision? So you can see that if you're training on T4, which are basically used for designed for inference, you would reduce from $180 to just under $120, and that is a very significant reduction in the training time. All of the code samples that I've showed are in my blog post. Some of them I just stole from NVIDIA's blog post. I will also put a link before I upload the presentation. And that's basically it. Do you have any questions?
One small question. You said that the multiplication and the division include the hyperparameter, right? So when you change the environment variable, is it constant, like a common value, or how do you? Okay,
so as I mentioned, there is a technique to find an optimal scaling factor, and in the backend, TensorFlow implemented this mechanism, so it kind of finds the optimal scaling factor
during the training.
During the training. It just sees if it gets vanishing readings and null values and infinite numbers, and if it does, it just reduces the number a little bit. If it stays constant, it tries to increase the scaling factor and kind of try to optimize it.
Is there a significant increase of memory when using higher batch sizes?
Okay, it's a good question. You mean obviously, if you're using the same, if you're using significant more batch sizes, you are putting more data into your network. The question would be if you're getting overhead when you're changing between a low number of a small batch size with floating point 32, as opposed to a much higher batch size with a floating point 16. So these are all can be very easily computed because you can actually know how much more data you're putting in if you're increasing if you're decreasing the representation to floating point 16 and increasing the bit size. You do have some kind of overhead with a redundancy because you are keeping some of the weights in floating point 32, and so it's not straightforward. It can go up to, I think, 8 times more representation if you didn't keep all of these duplicate weight copies. Hope answers your question.
What happens if you want to do mixed precision during inference? I mean, do you have to do the same? I mean, you don't have any as a gradient, but can you reduce, I mean, even more the
Yes, mixed precision also very good for using on inference. For this, you only have to cast the variables and then just do the forward propagation because you don't compute gradients.
Right, but I mean, can you reduce the weights even more? I mean, part of what you said is that part of the problem during training is that when you update the weights, right?
Mm-hmm.
So during inference, can you maybe use floating point 8 or can you reduce it even more?
Oh, you said, I mean, yeah. So this is like, first of all, you don't have, the main advantage of using floating point 16 is that
Support.
you have a register that supports floating point 16. Why did NVidia didn't go to floating point 8? I think like this would be the reason because it would result in a much nearer margin, and you would be able to represent very typical weights and activations.
So you showed us the code for a simple calculation, but I guess for a GAN you would have 2 different setups, one for the generator and one for the...
Yes. So basically we have here our code sample in Medium. It doesn't change a lot.
Yeah, that's the question.
It doesn't change a lot because a GAN is a convnet and an upsamplenet. Basically, it is. You can add a classifier to it. So we went through all of the changes you have to do in the generator and the discriminator. You have a full code that we created, and also this is all for TensorFlow 1. If you're using TensorFlow 2, then the whole change you have to do is just flip on the training flag.
Have you tried it on Google's Tensor?
TPU.
Tensor, yeah, the TPU.
Okay, TPUs are more interesting. I didn't mention TPUs. They're a very strong competition to Tensor Cores. They show very, very similar results. For some use cases, TPUs are much better. For some use cases, NVIDIA is doing better. Google is using floating point 16b. They kind of figure out that most of your gradients, they're kind of doing the scaling automatically. Most of your gradients or your parameters or your numbers in the network do not use all of the representation, kind of what you see here.
Is it also relevant to Google Colab?
Yeah, in Google Colab you can get a TPU, and TPUs kind of solve automatically the problem of this representation because they reduce, they give less spots for the, אני לא בטוח איך אומרים את זה, כאילו, כן, כאילו למספר השלם אתה מקבל פחות ייצוג ולאחרי הנקודה הסרונית אתה מקבל יותר ייצוג ואז יש לך שם, כאילו אתה מקבל בחינם את התהליך הזה שאתה עושה כאן.
אבל הוא מוגבל מבחינת ה-GPU עם הקולאב.
הקולאב הוא הדרך חינמית לקבל TPU, אתה יכול...
יש לך איזשהו limitation מבחינת המשאבים שאתה יכול לדרוש שם.
So the question is if Colab, if TPUs are limited. So Colab are used for experimental or educational purposes. So if you want to get a free TPU for an hour or so, you can use a call. I'm not sure like the limitation exactly. If you're using it for commercial use and you want to you do that, you can definitely use Google Cloud and you get a TPU. It would after you finish training after you finish developing your model, running massive networks on TPU could be substantially cheaper than training on a standard GPU because the operations, as you can see, are reduced. Assuming that the TPU is compatible with a reduction that we see with a Volta architecture, then the reduction can result in more than 60% of the cost, and that would compensate for the high cost of TPUs.
You mentioned that in TensorFlow 2 you have to set a flag in order to activate the mixed precision.
Mm-hmm.
Is there a reason why not doing it if by the GPU supports it?
Yeah. For example, you start developing your network and you activate the flag, and you start to submit the training, and for some reason your loss gets exploded. You get exploding gradients or vanishing gradients. So you might look at your architecture, and perhaps Google did not, or TensorFlow did not write a good enough optimization for your case for the loss scaling, or perhaps you're using an activation that does not really support well the mixed precision training. So you'd have to kind of overcome this. So if you're kind of getting strange results when you're trying to just activate the flag and train your network, then you might gonna go deeper into what TensorFlow has inside and see where did you find the problem. But for the most part, I think no. טוב, אז אם שאלות, המון תודה.
Oof.